Okay, so in this video, we will consider our third and final setup in counting. The problem is the same as before. We want to count the number of ways in which R elements may be selected from a set containing n elements. If you remember setup 2, it was ordered without replacement. Here the difference is that now we have an unordered selection. So let's see how this will affect the total number of possible outcomes. So again, we have n elements to choose from. Visualize those elements as balls numbered from 1 to n. And out of those n balls, we are selecting r of them. And the total number of possible outcomes, so the total number of ways in selecting those r elements from the n given elements in an unordered fashion and without replacement, we give this a special name. It is denoted by n CR, and this reads n choose R. So the total number of ways in which R elements can be selected from a set of n elements when the selection is unordered and without replacement. This is a little trickier to count, so let's start first with a simple case where we only select 3 elements. So n is any n, could be 10, could be a million. But let's consider only choosing 3 elements from our set. And here we'll compare the number that would be obtained from setup 2 and setup 3 to see how close they are to each other. And what we'll find out is that this number is a multiple of the number NPR and vice versa. So let's compare both. Setup 2 NPR would be ordered Of course, setup 3 now, it is unordered. So let's see. We're choosing 3 elements, and suppose, just for argument's sake, that the ones that were chosen were balls 1, 2, and 3. Now think of the possibilities if you have an ordered selection, as in setup number 2. And remember, both setup number 2 and number 3 are without replacement. The only difference is setup number 2 is an ordered selection. Setup number 3 is an unordered selection. So suppose balls 1, 2, and 3 were chosen, and now we have an ordered selection. Look at all possibilities. It could be ball number 1, then 2, then 3. Or it could be ball number 1, then 3, then 2. Or it could be ball number 2, then 1, then 3. Or ball number 2, then 3, then 1. Or ball number 3, then 1, then 2. And finally, ball number 3, then 2, then 1. All of these, even though they all contain ball number 1, 2, and 3, are different selections, as in setup number 2, we keep track of the order of the selection. So here there are 6 possibilities. But now imagine what happens to all of these 6 selections if we now consider them as being unordered. Well, they all become the same selection. Every selection here contains the balls 1, 2, and 3. So those 6 selections become only one selection when the setup is unordered. And that is our key observation here. So clearly, NPR is bigger than NCR, right? So this would be NP3 as we selected 3 elements. So we can see that NP3 is, well, there's 1, those 6. So for every given selection that is unordered, we get 6 different selections that are ordered. So NPR is 6 times bigger than, or I should say NP3, because here we said let's pick 3. NP3 is 6 times bigger than NC3. Now let's try to understand how this 6 can be viewed as a function of the 3. And then we'll be able to generalize and see that we'll have a result about r equals 3, but it will obviously be always true for any given value of r, whether r was 1, 2, 3, 4, 5, and so on. Let's try and understand how can 6 be viewed naturally as a function of 3. So we have our elements, 1, 2, 3. And now imagine the following question. What is the number of ways in which these 3 elements can be ordered? So there's the first element, there's the second, and there's the third. There were 3 balls, number 1, 2, and 3. And we're asking in how many ways can we rearrange these 3 elements? Well, for the first pick, we have 3 possibilities. But once you pick which ball is first, if you look here, is it going to be ball number 1, or ball number 2, or ball number 3? Because it is without replacement, then this ball can't be used again for the second pick, so it's gone, which leaves us with only 2 options for the second pick. But once you pick the first and the second, then 2 options are gone, which leaves you with a single ball. So when you reorder those 3 elements, you have 3 options for the first pick, then 2 for the second, then 1 for the third. So in total, we're saying 3 and 2 and 1. We are saying 3 times 2 times 1, which equals 6. Aha! But we can view 6 as 3 factorial. So in general, or at least I should say in this case, there are 3 factorial ways to rearrange the 3 elements. And so in general, the argument would be the same if you had 4 balls. You'd have 4 options for the first, then 3 for the second, then 2 for the third, then 1 for the fourth. So in general, there are r factorial ways of rearranging r elements. And with this now we're good to go, right? So we can now replace the 6 by the 3 factorial, and so what this will become is NP3 is, and now we don't view 6 as 6 but as 3 factorial, so NP3 is 3 factorial times NC3. And as we've said, this is a special case, but it's always true. You can replace 3 by any number and the argument is the same because there are always r factorial ways of rearranging r elements. So in general, NPR is r factorial times NCR. And then we can write this as a simple mathematical equality, right? So what is the implication here? NPR is r factorial times NCR. But think of this equality. We know what NPR is. We've already found it in the previous video. R factorial we know how to calculate, so we can easily isolate NCR by dividing across by R factorial. So divide both sides by R factorial. These two will cancel, and you have now isolated NCR. NCR, the total number of ways of selecting R elements from a set of n elements when the selection is unordered and without replacement, is simply NPR over R factorial. And if you want, you can write this as using the factorial only, as NPR is a function of the factorial. So if you remember, NPR was n factorial over n minus r factorial. And if you divide NPR, which is this number, by r factorial, if you divide a fraction by an integer, you simply squeeze it in its denominator. And so this is now NCR as a function of NPR or as a function of the factorial only. So there you go. But now we don't even need those two expressions, as there's a shortcut key for NCR on the calculator. But be aware that this can be obtained from the factorial. So let's try this out now. Let's do one example. Let's calculate, say, NC5. Whoops. NC5. And again, we are asking here for the total number of ways of selecting 5 elements from a set of 9 elements when our selection is unordered and without replacement. Well, let's use the shortcut key in our calculator first. So again, here's a standard sharp calculator, and you'll see that the NCR, the shortcut key is above 5, NCR. So here we're saying 9, so press 9. The NCR is above the key of 5, so you have to use the second function, 5. Then you have 9C, and it is 9C5, so press 5. And you'll get that 9C5 is 126. So there are 126 ways of selecting 5 elements from 9 elements when the selection is unordered and without replacement. Or of course, if you wanted, you could use the factorial exclusively. 9C5 is 9 factorial over n minus r, 9 minus 5 is 4, 4 factorial, r is 5, 5 factorial. So if you do 9 factorial over 4 factorial times 5 factorial, you will arrive at the same answer, 126 different possibilities. And that's it. So now let's consider an example of this. So here's the problem. We are saying that a box contains 17 watches and 6 are defective. So naturally 11 are non-defective. If you select 5 watches at random, then in how many ways can you obtain A, 5 watches, B, not a single defective watch, C, exactly 3 defective watches, D, at least 2 defective watches? Now if you look at the problem here, first, we are saying that we have 17 watches and we are selecting 5 of them. So implicitly here, it is without replacement. So there's a box with 17 watches, you select 5, implicitly again, without replacement. And if you look at the type of questions that we're asking, we're only asking, okay, in your selection of 5 watches, how many are defective? Is it none? Is it 1? Is it 2? Is it 3? Is it 4? Or is it 5? And we're not concerned with, well, which one was defective? Suppose we look and say there are 2 defective watches. Well, was it the first and the third that was selected? Was it the fourth and the fifth? Was it the second and third? Which 2 were the defective ones? And it doesn't look like we care here. We're only asking, okay, you have this box of watches, there are 17 of them, select 5 at random, how many are defective? We don't care which one is or which ones are defective, only the total number of defective watches, which means that we do not care about the order of the selection. So here we have an unordered setup. Which is exactly setup number 3, an unordered selection with that replacement. So we're good to go. Let's visualize our box. And we'll visualize the box as a simple Venn diagram. So we have our total number of watches is 17. And they're split up into 2 types, defective and non-defective. I will use D for defective, and there are 6 defective watches. Of course, non-defective is the opposite of defective, which can be viewed as the complement of being defective. So D complement. And there are, of course, 11 of those. The total must be 17. Okay, and because, as we've said, it is an unordered selection without replacement, we will obviously use here N choose R. Okay. So we were asking in part A, in how many ways can you obtain 5 watches? So here we're saying we don't care defective or non-defective. You have 17 watches, you select 5 at random. What is the total number of ways of selecting those 5 watches? Well, what is N? The total number of elements to choose from. Well, here there are 17, so out of these 17 available watches, we are choosing 5. So it's just 17 choose 5. Use the shortcut key on your calculator, and you will arrive at a total number of possible selections of 6,188. Different ways of selecting at random 5 watches from the total number of 17 watches, again, having an unordered selection and without replacement. B, in how many ways can you obtain not a single defective watch? Okay, well, think of it this way. If you say that you have not a single defective watch, it means that you have 5 non-defective, and 0 defective watches. Let's write that down. Not a single defective watch means that we've selected 0 defective watches, and because in total we are choosing 5 watches, so 0 defective watches and 5 non-defective watches. So that's what we're asking for, right? The total number of ways in which you can select 0 defective watch and 5 non-defective watches, which means that not a single defective watch has been selected. Well, let's think about this. We have to choose out of the defective watches 0. So, out of the 6 defective watches, we are choosing none, and n means multiplication, and times out of the 11 non-defective watches, we are choosing 5. and that is our total number of possibilities. Out of the 6 defective watches, we are choosing none, and out of the 11 non-defective watches, we are choosing 5. And if you calculate this, you will arrive at 462 different possible ways of selecting not a single defective watch out of the 17 watches. So if you're ever unsure about how to count a given selection, always write it down. Not a single defective watch is being selected means that out of the defective ones, we choose 0, and times out of the non-defective watches, we choose 5. So 6 choose 0 times 11 choose 5. Let's look at C now. In how many ways can we choose exactly 3 defective watches? Well, now we are saying we have to choose 3 defective watches, but we are choosing a total number of 5 watches. So you can't just say 3 defective watches, therefore 6 choose 3. Because if all you give me is 6 choose 3, you've only selected 3 watches. But we are always choosing in total 5 watches. So if we are saying exactly 3 defective watches, it means 3 defective watches and, of course, 2 non-defective watches. Because in total we are always choosing 5 watches. So always make sure that when you're counting, that in your hands you have a complete selection. 3 defective watches means 3 defective watches and 2 non-defective watches, and now we can count the total number of such possibilities. Okay, defective watches. Out of the 6 defective watches, we are choosing 3, and out of the 11 non-defective watches, we are choosing 2. And now you have a complete selection of 5 watches, 3 coming from the defective ones, 2 coming from the non-defective ones. And again, if you calculate this with your calculator, you will arrive at 1,100 possible such selections. And that's it. For C, D is a bit more interesting. And in D, I am asked you to provide 2 different solutions, just to see that there is essentially one nice way of answering D and one not so nice way of answering D. We'll start with the rather bad solution. Okay, so we're asking, in how many ways can we obtain at least 2 defective watches? Well, what does that mean? Well, let's start with looking at the total number of possibilities. We are selecting 5 watches. There are 6 in total that are defective, so we could have, for the number of defective watches in our selection, 0, or 1, or 2, or 3, or 4, or 5 could be defective. Our event here is at least 2 are defective. So 2 or more, so 2, 3, 4, or 5. And right away when you see this, you should look at, well, the event A is bigger than its complement, so here naturally we should use the complement rule. But first let's be naive, let's compute this brute force, but then we'll realize that in half the work, we'll get the same answer using the complement rule. So here the bad solution is the direct one, the good one is using the complement rule. Okay, so let's count this directly, brute force. So if you're saying at least 2 defective watches, then you are saying exactly 2, or exactly 3, or exactly 4, or exactly 5. We're saying or, that's a partition, which means pluses. Let's start with the number of ways of selecting exactly 2 defective watches. Well, Out of the, and remember there are 6 defective watches, so out of the 6 defective watches, we are choosing 2, which means that out of the 11 non-defective, we are choosing a remaining 3, as in total, there must be 5 watches in our hand. So this is the total number of ways of choosing exactly 2 defective watches, and therefore 3 non-defective watches. Or, there could be 3 defective watches. So, or plus. Well, out of the 6 defective ones, we choose 3. Therefore, out of the 11 non-defective, we choose the remaining 2. As again, we are choosing 5 watches in total. Or, there could be 4 defective watches. So out of the 6 defective ones, we choose the 4, and therefore out of the 11 non-defective, we choose the remaining 1. As again, there are 5 watches being picked in total. Or, finally, there could be exactly 5 defective watches. So out of the 6 defective watches, we choose 5, and out of the 11, we choose none, as we already have selected our 5 watches. So if you add all of this up, you will obtain 3,746 different ways of selecting at least 2 defective watches. Exactly 2 defective, or 3, or 4, or 5. And again, because of the keyword OR here, it means a partition, therefore an addition of all possibilities. That's our first solution. Brute force, not very efficient. Let's now be clever about this. Let's use the complement rule. So let's start back now. So we had all possibilities up to 5. We wanted to count those possibilities. Well, let's first count everything. The total number of possible selections we already know is 17 choose 5. So total number of ways of selecting 5 watches from the 17 minus, well, we want to be left with this, so minus what we don't want. So minus 0 defective watches, which means out of the 6 that are defective, we choose 0. And therefore, out of the 11 non-defective, we choose 5. We have to remove this case as well, so minus again, choosing 1 defective watch. Therefore, out of the 6 defective ones, we choose 1. And out of the 11, we must choose 4, as we are choosing 5 watches in total. And now we're done. We've added every possible selection and removed the cases where we had no defective watch and 1 defective watch, and so that leaves us with the cases where 2 or more watches are defective, which is the event of interest. And if you calculate this on your calculator, which is basically half the work of the original solution, you will arrive at the exact same answer, 3,746 different ways of selecting at least 2 defective watches. And that's it. So, in conclusion, every time you have a counting problem, we have our 3 fundamental setups. So always ask yourself, is the selection ordered or unordered, with or without replacement? Then you'll know under which setup you are, and then you can count the total number of possibilities quite easily, either using enter the R, NPR, or and choose R. And always be careful that when you have a selection, that you make sure that you have in your hands, in the end, a complete selection. And if you're ever unsure, just write down what the selection implies, or say it in your head, and that way you'll always remember to have a complete selection. When you say and, you will multiply. When you say or, 2 or 3 or 4 or 5, you will add. And this way, it will make counting problems very straightforward. And that's it.